Hello everyone. So this is the video on the chapter 1 solid state. So we are beginning with the classification of solids. You know the solids are classified into two categories. The first one is crystalline solid and the second one is amorphous solid. Now some differences we can see between these two. First one is crystalline solids have regular internal arrangement of particles, whereas amorphous solids have irregular internal arrangement of particles. All crystalline solids have sharp melting point, whereas amorphous solids melt over a range of temperature. Third one is crystalline solids are regarded as true solids. Amorphous solids are regarded as supercooled liquids or pseudo solids. Now, the fourth point for crystalline solids is that these undergo a regular cut, where amorphous solids undergo irregular cut. And the last difference between the two, that crystalline solids are anisotropic in nature, whereas amorphous solids are isotropic in nature. Now, let us study the crystal lattice. How can we define crystal lattice? It is a regular ordered arrangement of constituent particles in 3 dimensions is called or known as crystal lattice, which is visible here in the diagram, and it is showing a portion of 3D cubic lattice and its unit cell. So students, I want to highlight here, specify here, the orange one part highlighting you are seeing is actually representing a unit cell, and the whole 3D arrangement is known as crystal lattice. Now the parameters which characterizes a unit cell. First one is dimensions of the unit cell along the 3 edges A, B and C. These edges may or may not be mutually perpendicular. Second is inclination of the edges to each other. This is denoted by the angle between the edges, alpha, beta and respectively gamma can be taken. Is the angle between the edges B and C? Beta is the angle between the edges A and C, and gamma is the angle between A and B, which is clearly visible in this diagram. Parameters which characterize a unit cell. Lattice points or lattice sites. The fixed positions on which the constituent particles are present are called lattice points or lattice sites. A group of lattice points which, when repeated over and over again in 3D dimensions, give the complete crystal lattice. And about unit cell, once again it is defined as the smallest repeating unit in space lattice, which when repeated over and over again generates the complete crystal lattice. The crystal can consist of an infinite number of unit cells. Now have a look over type of unit cell. First one is primitive or the simple unit cell. Have constituent particles only at its corners. Second, centered unit cells are those unit cells in which one or more constituent particles are present at positions in addition to those present at the corners. Now, types of centered unit cells. First, face centered unit cell. It consists of one constituent particle present at the center of each face in addition to those present at the corners. Second, body-centered unit cell. It consists of a one constituent particle present at its body center in addition to those present at the corners. Here, diagrammatic presentation will show all 7 types of primitive unit cells. This is also known as 7 crystal system. So here, students, you can see the first simple cubic, and parameters are characterizing this unit cell itself. There A is equals to B and B is equals to C and are perpendicular on each other. Second one is tetragonal, where A is equals to B but B is not equals to C. But the angles are 90 degrees. Orthorhombic, none of the edge length are equal to each other, but the angles are 90 between them. Hexagonal, A is equals to B but B is not equals to C, where gamma specifically is 120 degrees. Rhomboidal, all the edge length are equal to each other. Alpha is equals to beta and beta is equals to gamma, but these are not equals to 90 degrees. Have a look on monoclinic, where A is equals to B but B is not equals to C, and see the angle beta is not equals to 90 degrees and rest are equal. Triclinic, and in triclinic you can find that none of the parameters are equal to each other and angles are not equals to each other and not equals to 90 degrees. Now this is the packing. You can see the pattern of arrangement. The first pattern shown here is ABAB type of pattern, and this lattice is called HCP. And another pattern is presented here, ABC pattern, and the lattice is called CCP or FCC, where you know students, HCP full form is hexagonal close packing, CCP full form is cubic close packing, and FCC's full form is face centered cubic close packing. Now this packing also produces or generates 2 types of voids. They are octahedral and tetrahedral voids. Number of octahedral voids are always equals to the number of effective atoms present in unit cell. However, the number of tetrahedral voids are twice the number of effective atoms present in unit cell. So, number of tetrahedral voids equals to 2 multiply number of octahedral voids can be written. Now have a look on the packing efficiency. What is packing efficiency? So packing efficiency is equals to volume occupied by all the atoms present in unit cell divided by total volume of unit cell, and this is multiplied to 100 in order to calculate percentage packing efficiency, which you can see in this table. The first column is closed structure. Closed structure of HCP and CCP or FCC contains number of atoms per unit cell Z, always 4. The relation between edge length and the radius of atom is given for this closed structure, and that is R is equals to A upon 2 root 2. Packing efficiency is 74%. For the next packing, that is BCC closed structure, number of atoms are 2. Relation between R and A is given as R equals to root 3 by 4A, where the percentage packing efficiency is 68%. And for the last simple cubic lattice, Z is 1. Relation is given R equals to A by 2 and the packing efficiency is 52.4%. So students, you can conclude here, that's very easy, that the most efficient packing is HCP and CCP or FCC. Thank you everyone.